A very good morning, students. So we are going to look and explore the second topic, which is end-to-end machine learning. In the previous topic, we understood what are the different types of machine learning algorithms. We spoke about supervised learning, we spoke about unsupervised learning, and semi-supervised learning algorithms. We also understood what is the hyperparameter, what is the need for a test set, what is the need for a validation set, what is overfitting, what is underfitting, and so on and so forth. While we do understand that the entire spectrum of machine learning has been covered theoretically, it is very important for every engineer to understand the steps and processes involved in engineering a real-life machine learning solution. With that in mind, let's proceed further to understand how do you engineer an end-to-end machine learning project. In this topic, you look at a project end-to-end and pretend that you're a recently hired data scientist in a real estate company. Some of the major things you'll go through are looking at the bigger picture, getting the data, discovering and visualizing the data to gain insights, preparing the data for machine learning algorithms, selecting a model and training it, fine-tuning the data, presenting the solution, and launching, monitoring, and maintaining the system. When you're learning about machine learning, it's actually ideal to experiment with real-world data and not just artificial data sets. Unfortunately, there are thousands of open data sets to choose from different kinds of domains. Here are some of the places where you could look into the data sets. There are popular open source data repositories like the UZ Irvine Machine Learning Repository, Kaggle datasets. Kaggle is essentially a platform where Google encourages people to pursue working on data science problems by giving them questions, data sets. They think of it as the equivalent of HackerRank, but for machine learning. Then there is Amazon AWS's datasets. There are some meta portals where they list open data repositories. And there are some other places where you can download data as well, like Quora, Wikipedia, and so on. In this particular topic, we choose the California housing prices dataset from the StatLib repository. The dataset is based on 1990 California census. It's not exactly recent, but there are many qualities that are very useful as far as this dataset is concerned, which can help for a teaching purpose. So this is the California housing price data as a function of location. As we said, you would imagine you've been welcomed into the Machine Learning Housing Corporation. So your first task is to build a model of the housing prices in California using the California census data. The data has metrics like the population, the median income, the median housing price, and so on for each block group in California. And block groups are basically the smallest geographical unit for which the Census Bureau publishes sample data. So basically, it contains a population of 600 to 3,000 people. You can think of them as a rough equivalent of districts. So your model should essentially learn from the data and predict the median housing price in any district once given all the other metrics. Okay? So since a well-organized data scientist, essentially approaches a machine learning problem sequentially by having a checklist, you can start with the one given later. Right? It's important that you understand that this checklist gives you an ordered way of approaching machine learning problems. The first question you ask your boss is exactly what the business objective is, right? Why are we developing this particular price prediction model? Building a model is not the end goal, right? So the company expects to use it in a certain way and benefit from the results of the model. It's important to know this because this helps you frame the problem, influences your choice of algorithms, and even the performance measure that you use to evaluate the model. And most importantly, the amount of effort you spend on treating it, right? Because accuracy that you achieve in the model is concomitant with the amount of time that you spend on fine-tuning the model. So POS usually answers that the model's output will be fed to another machine learning system, right? The prediction of the house price, and along with some other signals. The downstream system will determine whether it's worth investing in a particular area or not. Right? Getting this right is critical because it directly affects the revenue of your company. So let's look at this particular diagram that has been given here. Right? So any piece of information that's fed to a machine learning system is called a signal. Right? So if you see, there's the district data here, database, and you see there are some upstream components which we are not concerned with. The prices are fetched from the district data. The district pricing is here, and once your model takes in information about the district, then it predicts the price. Right? Prices are then stored here, and then these prices are used along with a set of other signals in making an investment analysis, and finally, the result as to whether it's worth investing in the real estate in this particular area is shared with the end user. Another essential concept that we need to visit through this is the pipelines. Pipeline is essentially nothing but a sequence of data processing components. Right? It's a data pipeline. It's very common in machine learning because there's a lot of data to manipulate and many data transformations to apply. So components typically run asynchronously. Right? Asynchronously means that they run independent of each other. Each component pulls in a large amount of data, processes it, and then spits out the result in another data store. Right? Then sometime later, next component in the pipeline pulls the data and spits it out into its own output. Right? So each component is fairly self-contained. The interface between components is simply the data store. So the system is very simple to grasp, right, with the help of a data flow graph, and different teams can focus on different components. So component breaks down, the downstream components can continue to run normally for a while, right, by using the last output from the broken component. So this makes the architecture very robust. So just to give a simple example of how this system would look, so assume that there is a sequence of systems as shown here, and then data enters like this, and this is the flow of data. Usually there will be system 1, system 2, and system 3. This is what is called a data pipeline. So a broken component can go unnoticed for some time if the proper monitoring is not implemented. So it's very important that you keep monitoring the overall performance of the system and find out if the data gets stale, right, or the system performance drops. So next question you need to do is to ask what the current solution looks like. Right? You obviously have a mechanism at present. It gives you a reference performance, essentially. For example, if he says, currently the price prediction has an accuracy of 90%. It tells you that the machine learning model that you need to build necessarily has to have an accuracy which is strictly greater than 90%. It's going to be lesser or equal. There's no point in exerting all this effort to build the model. Right? So your boss answers the question that the district housing prices are currently estimated manually by experts, and a team gathers up-to-date information about a district, including a lot of parameters and excluding the median housing prices, and then they use complex rules to come up with an estimate. It's very costly and time-consuming, and the estimates are not great. Typically, the error rate is 15%. It means the accuracy is just 85% in these cases. It's very important for you to understand this metric so that you're really able to build a system that has accuracy rate which is much higher than the current process. And also at the same time, it's important for you to understand the need for automation here, because currently a lot of effort, particularly human resources, is being expended in order to produce this output that can be quite saved on if you build a machine learning engine to do the same. Now, with all this information, you're quite ready to start designing the program. So the first thing you need to do is to frame the problem. Is it a supervised learning program? Is it an unsupervised or a reinforcement? Let's take a bit of time to revisit the concepts from the first chapter. If you remember supervised learning, right? Supervised learning is when you have the input, right, and the output, right? You have the input and the output, right, for a set of entries, and you're trying to predict the output for a new entry based on the input. So it's like pattern recognition, right? You keep on seeing a lot of inputs and their corresponding outputs. And finally, you're given a new input, you predict the right output. Right? So this reminds you of supervised learning. So you can say that the price prediction for real estate in this particular example is supervised learning. You can even go one bit further to say it is linear regression, because we're using a linear equation to mathematically model the prices as a variable of so many factors, an equation containing so many variables, and these variables essentially determine the price of real estate. Now, so it's a typical supervised learning task, as I said, because you're given labeled training examples, right? Each instance comes with the expected output, which is in this case, the district's median housing price. It's also a linear regression task or a regression task because you're asked to predict a value. You're not asked to classify, you're asked to predict. So more specifically, this is multivariate regression. Multivariate means there are multiple variables involved in the process, and the system will use multiple features to make a prediction, right? The district population, the median income, and so on. So in the first topic, you predicted a life satisfaction just based on one feature, which is GDP per capita, right? So it's a univariate regression problem, right? And there was no continuous data coming into the system, so there's no particular need to adjust the data rapidly. So the data is small enough to fit into the memory. So plain batch learning should do this time. The data is huge. What you could do is you either split your batch learning work across multiple servers, right? You have the map reduce technique, which you'll see in subsequent units, or you could use an online learning technique, as you remember from chapter. Now, at this point, it's important we take a step to understand what we have done so far, right? We have seen that we have a particular data that we have extracted, right? And we are trying to use the data to build a linear regression, multivariate linear regression model, right? Multivariate linear regression model, which has the ability to predict real estate prices, median housing price based on certain parameters. It's a supervised learning task. So at this point, you have to understand what the performance measure is. So the performance measure particularly used for linear regression problems is the RMSE, or the root mean square error. So it measures the standard deviation of the errors the system makes in its prediction. And RMSE is equal to 50,000, means 68% of the system's predictions fall within $50,000 of the actual value. About 95% of the predictions fall within $100,000 of the actual value, right? Let's look at a small bit of statistics for you guys to remember. So this is the standard distribution, right? Standard distribution, the deviation from the mean is the center, one standard distribution and standard deviation away, you get 68% of the data is covered. And two standard deviations away, you have which is basically 46 into 2. It's 92%. So 92% of the data is covered here. In some cases, they model it as 34 plus 40 rather than 12, in which case we can say that 96%. And the remaining after two standard deviations, that is beyond two standard deviations, right? The remaining percentage of the data is 4%, 2% on either sides. Now, this is essentially what RMSE does here. So what we do is we take each data point. So assume that you have X is the input space. Your predicting function is H. So H of X becomes your predicted output. The predicted output. and say y is the actual output. So y is the actual output. Now, how RMSE is measured essentially is that for each value of the predicted output, you subtract the actual output. Right? You cannot directly add this because each one will have positive and negative signs and they may cancel each other. So you square the output. Right? Only way to remove negative signs is either by squaring or by taking absolute value. In the case of RMSE, you choose to square, right? So you square it and then you take the average. You take the average, where M here is essentially the number of observations. It's the number of observations. Basically, the size of the inputs training set. So then you take a square root. So this is RM, let's see, root means square. Okay. So I repeat, we are once again referencing the concept of a standard distribution. So in a standard distribution, the split is basically 34, 34, 14, 14, 2, 2. Right? So this is the mean, and then we usually have mean plus 1 standard deviation here, and mean plus 2 standard deviations here. Right? So this is the formula of the root mean square error. Hope this is clear. So let's move on further. So here there is just a revision of what exactly we looked into earlier. M is the number of instances in the data set in which you're measuring RMSE. So for example, if you're evaluating RMSE on a set of 2000 districts, then we say M is 2000. Right? It's X is the vector of all the feature values of the ith instance of the data set, right? That's why we say Xi, and Yi is the label, basically the desired output. So, for example, if the first district in the data set is located at this latitude, this longitude, has these many inhabitants, and the median income is this, and median housing value is this, right? And what is the Xi? Xi is essentially all the possible inputs. So the inputs are everything but for the median housing value, because that is the output. So basically you have your latitude, your longitude, the number of inhabitants, and the median income, which is what's been modeled here. And then you see Yi is the predicted output. Sorry, I mean the actual output. Okay? Yi represents the actual output. Which in this case is 156,400. We see X is a matrix containing all the feature values, right, of all instances in the data set. There is one row per instance, and the ith row is equal to the transpose of Xi, noted by Xi transpose. So if you had the data represented in X as this, each element is the transpose of the X vector, so it is represented and shown here. H is your system's prediction function, which is also called the hypothesis. So when your system is given an instance's feature vector xi, it outputs a predicted value h of xi for that instance. So if your system predicts that the median housing price in the first district is 158,400, right? And the prediction error is 2,000. Why? Because 156,400 is the actual price, and the predicted price varies from it by a magnitude of 2,000. RMSE x comma h is the cost function measured on a set of examples using the hypothesis. So we use lowercase italic generally for scalar values and function names, and lowercase bold fonts for vectors, and uppercase bold fonts for matrices. Right? So even though we use RMSE as the preferred method of performance for regression tasks, in some context, you tend to use another function. So in this cases, particularly if there are many outlier districts, you may consider using the mean absolute error. So as I mentioned earlier, right, when you subtract hx minus y, you can directly not add them because some of them will be positive, some would be negative. So one way would be to square it, which was an RMSE. The other way would be to take the absolute value, which is what is being done in MA. So remember, generally when there are more outliers, outliers mean that if, for example, you have this data set, this is the mean, most of them are around the mean, but there is one point here. Now, the distance between the mean and this gets squared up in RMSE. So any outliers impact on RMSE will be very high because the term is squared. Whereas in MAE, because you're not having a square dependency but a linear dependency, the impact of an outlier is lower. So that's why particularly whenever there are more number of outliers in the data set, we prefer to use mean absolute error in place of RMSE. But RMSE and ME are both ways to measure the distance between two vectors. So the vector of prediction and the vector of target. So whereas distance measures or norms are possible, right? Computing the root of a sum of squares, RMSE, corresponds to the Euclidean norm, right? The notion of distance that you're familiar with. Basically, you have 2 points, x1, y1, x2, y2. Then we know by coordinate geometry that the distance between them is x2 minus x1 the whole square plus y2 minus y1 the whole square root. So this is the distance, the Cartesian distance between 2 points. Now, computing the sum of the absolute values corresponds to the L1 norm. Right? It's called the Manhattan norm because it measures the distance between 2 points in a city. Right? Because, for example, say you had 2 points in a city, right? There's one here and there's one here. Generally, just subtract them. There's no squaring business, right? That's why it's called the Manhattan norm because it is concomitant with how you do it in the real world. Generally, of course, you can generalize the entire process, right? L1 and L2 were the norms we saw. If you see LK, the norm LK is nothing but VO power K, V1 power K plus up until Vn mod power K, the whole power 1 by K. Right? So it's the LK norm, LK, right? And L0 just gives the cardinality of the vector. L infinity gives the maximum absolute value of the vector. Why L0? Because, for example, if you take V of 0, all the powers inside would be 1. So 1 power k, which will essentially be 1, will go on up till the number of elements of the vector, which is essentially the cardinality. So the answer would essentially be 1 so many times, so n power 1 by k. And now here we know that this would give you the cardinality of the process. Okay? It's cardinality of the entire set. So I repeat once again, L0 gives the cardinality. L infinity is the maximum absolute value. And the higher the norm index, the more it focuses on large values and neglects smaller ones. That's why RMSE is more sensitive to outliers than ME. When outliers are exponentially rare, then RMSE performs better. Just keep this in mind. Next thing that we need to do is essentially, it's a good practice to understand and verify the assumptions that were made, right, so we can catch serious issues early on, like the district prices that your system outputs are going to be fed into a downstream machine learning system. And we assume that these prices are going to be used as such. But what if the downstream system just converts the prices into categories like cheap, medium, or expensive, and then uses this category system of the prices directly? In this case, if you're getting the price perfectly right, is not that important. Only the range is important, right? So it's more of a classification task, not a regression task. So you don't want to be working on a regression system to begin with. So fortunately, after talking to your team in charge, you find out that they do need the actual prices. So great, you're set, and you can start coding them. So to create the workspace, you need to have Python installed. It's already probably installed in your system. If not, you can visit the official Python website to install Python into the system. Right? And you need to create a workspace directory for your machine learning code and databases. You can open a terminal and type the following commands. Export ml underscore path equal to home, where you change the path if you prefer, and then you make the directory ml path. You install a couple of Python modules. Pip is essentially the way to Python's own packaging system, which helps with the distribution of Python binary installers. And once you've done that, you've successfully installed pip. You create an isolated environment, right? Because if you're working on different projects, they're having conflicting library versions, you can use virtual env. That's been explained here. So once you create the virtual env, you can activate it. Then you install the required libraries as shown here. As the library has been installed, all you need to do is basically just fire up the command Jupyter space notebook. Jupyter server is now running in your terminal to probably port 8888. You visit the server by just opening the web browser to the localhost :8888. Automatically happens when you run the command and you see the empty workspace directory. So now you create a new Python notebook by clicking on the new button and selecting the appropriate Python version. So it creates a new notebook file called untitled.ipynb in your workspace, starts a Jupyter Python kernel to run the notebook, and it opens this notebook in a new tab. So you should start by renaming the notebook to housing in this case, and this will automatically rename the file to housing.ipynb by clicking the untitled and typing it in. It's also possible. This is how the Jupyter Notebook terminal should look like once the installation has been completed. A notebook containing a list of cells, right, in general, and each cell can execute code. So right now the notebook contains only one empty code cell, labeled line 1. And by typing print hello world at the cell and clicking on the play button or shift enter, you can see that the line is executed. And a new line is created for code. So generally, in a typical environment, your data needs to be available in a relational database or across multiple tables, documents, and files. You first need to get your credentials and access authorizations and familiarize yourself with the data schema. But in this project, things are usually much simpler. So what you need to do is to download a compressed file called housing.pgz, which contains a comma-separated CSV file called housing.csv with all the data. And you could use your web browser to download it and run tar xzf housing.pgz to decompress the file and extract the CSV file. But it's preferable to create a small function to do that, which is useful in the case the data is changing regularly, right? So you have a small script that can always fetch the latest data, or you can schedule it. So here's a function to fetch the data that was created here, which we'll be briefly going through. Essentially, in the function, what you do here is you check if the path is there in the directory. If it is there, then fine, otherwise you create it. Then you create the TGZ path, you retrieve the URL, you download, extract, and then close. So when you call the fetch underscore housing underscore data, it creates the dataset slash housing directory in your workspace, downloads the housing TGZ file, and extracts the housing.csv from the directory. So you load the data using pandas, right? And a small function is shown here to load the data from the file. So def load underscore housing underscore data, right? CSV underscore path, OS path join, you give the path, and then pd.read underscore CSV. Function returns a pandas data frame, right, which contains the entire data. So this is how the data looks, right? If you do housing equal to load underscore housing underscore data and housing.head, this is exactly what you will see on your notebook screen. So each row here represents one district, and there are 10 attributes. You can see the first 6, and scroll to the side to see the remaining. The info method is generally used to get an information of the different type of attribute values and the data types in the data. So in this case, there are 20,640 instances, which is pretty small by machine learning standards, but it's good to get started. And the total bedrooms attribute has only 20,433 non-null values, meaning that 207 districts are missing the feature. Right? We need to take care of that later. And the attributes are numerical, except for the ocean underscore proximity field, and its type is object, so it can hold any kind of Python object. But since you've loaded the data from a CSV file, it must be a text attribute, right? So you see housing of ocean underscore proximity dot value counts contains all the features as shown here. Okay. There are other fields which you can see using the describe method. So the count, mean, min, max rows are self-explanatory, right? We have a percentile role as well. Another quick way to get a feeling of the type of data you're dealing with is to plot a histogram for each numerical attribute. So it shows the number of instances on the vertical axis that have a given range of value. You can plot this one attribute at a time, or you can just call the hist method on the entire data set and plot a histogram for each numerical attribute. Okay? So that's exactly what we're doing here. You see the histograms for different data distributions, the different columns. Okay.